Good afternoon, everyone, and welcome to Artificial Intelligence, Accessible Potential. My name is Matt Hackert. I'm the IT Access Program Specialist here with the Maryland Department of Disabilities, who is hosting this webinar today. Again, I want to thank you for joining. So this is my first presentation working with MDTAP, so I'm excited to be here. Excited to present this material. I will just start quickly with the disclaimer that while definitely an access technology specialist, not as much of an expert in AI, but certainly an informed enthusiast. So hope you enjoy the presentation and find some interesting information. Once again, our webinar this afternoon is hosted by the Maryland Department of Disabilities, Maryland TAP, the Technology Assistance Program, IT Accessibility Initiative. So I want to just take care of a couple of housekeeping things really quick. First of all, just informing everyone that this webinar is being recorded, and we will be posting it on the MDTAP YouTube channel in a couple of days. So if there's anything that you missed or want to watch again, it will be available in a couple of days' time. Our captioning is brought to you by AI Media, so I want to express our thanks to them. So you can access the captioning through Zoom. And also want to just mention, give a quick overview of our run of show this afternoon, that we will have, as time permitting, have a question and answer at the end, and I'll do my best to answer questions, keeping in mind my expertise is much more in accessibility and much more enthusiasm and interest in AI as a subject. But we'll start with an overview of AI, and I'll talk about a brief history in its developments and milestones, some of the things that have been accomplished. Then we will have an overview of accessibility, which again, you may have some knowledge about already. And what we really want to cover is where can current AI be leveraged to overcome accessibility issues, and what are its limitations, and so what does its future look like, and what does the future hold, which is always a difficult prediction to make, and AI itself has been fraught with challenges there, but we'll do our best and make an educated guess about it. So let's go ahead and jump right in with the material then, and we will start by giving a little bit of an overview about artificial intelligence and its history. The birth of artificial intelligence is really closely linked with the birth of electronic programmable computers. A lot of the work began in the 1930s and 1940s with figures such as Kurt Gödel, Alonzo Church, and Alan Turing. There was a lot of theoretical work done in those early days, talking about what the limits of mathematics are, what the limits of doing mathematics with machines. And then we look at some of the early computing devices. Computing first kind of started its inception kind of around the time of World War II, and there are a lot of applications with the mathematics for missile trajectories, and applications in radar, and applications in code breaking. I would recommend anybody interested can do some research on Bletchley Park, and a lot of the work that Alan Turing did breaking Nazi codes during World War II is actually really fascinating, but a little outside of the scope here. So we'll kind of continue on. During that time is when some of the first actual computers were built. Keep in mind that at that time, these were colossal machines. full of vacuum tubes, put out tremendous amounts of heat. We're very prone to breakdowns. I'm sure everybody's familiar with the term debugging, but a little bit of history that term actually has its origins in literally getting bugs, moths, and things out of the inner workings of the computers because they would short circuit things. They would cause vacuum tubes to burn out and so forth. Moving forward to 1956, there's a summer conference at Dartmouth College, which is a 2-month kind of brainstorming session with mathematicians and other scientists who got together to discuss the potential idea of quote unquote thinking machines. So discussions focused around computers, natural language processing, neural networks, theory of computation, abstraction, and creativity. The conference didn't formalize any specific conclusions per se, but rather it was really a springboard for initiating research in several branches of artificial intelligence. So this is really where we consider the term artificial intelligence to come from, is this conference at Dartmouth. And a lot of exciting discussion again about how things might proceed. So a lot of the history again goes hand in hand with the development of computers themselves. But it's remarkable to think, given the time, again, keeping in mind the infancy of computers themselves, there was no such thing as personal computers. These machines for millions of dollars, consumed great quantities of power, and were very slow and archaic, of course, compared to today's standards, maybe roughly equivalent to a 4-function pocket calculator today. And even that, I don't know, may or may not be a fair comparison. So we'll talk about then the early goals of artificial intelligence, and goals are also kind of some of the traits that we would expect to observe from a quote intelligent system. So we start with reasoning and problem solving, planning and decision making. So these are skills or traits that we observe in game theory. A lot of work early on was done in playing strategy games. Checkers, chess, Go are very well-known examples. Researchers began with building algorithms that mimic humans' skills in problem solving and reasoning, and the step-by-step approach that we take to problem solving. And then later, as things developed and computer power increased, approaches in the 1980s and 1990s incorporated concepts from probability theory and economics that could cope with greater uncertainty or incomplete information. So much more real world scenarios. Whereas chess and Go, the rules are very finite and limited. The number of positions are limited, and the system can have complete knowledge about the full state of everything. Really, the only uncertainty is what the opponent's next move would be. But even there, the system can calculate a best guess as to what the best move might be for their opponent to take and how it might respond. Then there's knowledge representation, and we'll come back to a lot of these concepts when we start talking about accessibility and accessibility problems. But knowledge representation has applications in clinical design, decision support, data mining, content-based indexing and retrieval. These are a lot of the things that have become much more familiar to us today. So think of Google search engine, think of a lot of the advances in the last decade or so around big data, data analytics, and so forth. Some of the problems, though, include difficulty in accumulating all of the quote common sense knowledge an average person knows. First of all, it's a surprisingly large amount of information, and so much of that information is difficult to express verbally or in a sense that a machine or a computer, as we understand it today, can understand or cope with. Another trait that we look for and a goal of artificial intelligence is various types of learning. There's been a lot of work done in both supervised and unsupervised learning, where systems have reward models in supervised learning. Unsupervised learning, there may be end goals in mind, and the computer can analyze data in a number of ways. Then categorization and regression learning. So taking a set of data and trying to, it's kind of like pattern recognition, seeing what kind of pattern it fits best to. Categorization is still a challenging problem in AI. A lot of the teaching that we provide to artificial intelligence systems has data already categorized into different classes. And then there's been different approaches in reinforced learning and then transfer learning. So once a system has mastered a set of skills, trying to teach it in various ways to transfer that to unique problems that it hasn't seen before. Of course, then there's been a lot of work done in robotics, which has not only challenges in learning and thinking, but there's physical challenges in building a device that can navigate in a real world environment. Natural language processing is a field that many of us are familiar with, especially with now assistants like Siri and Alexa and so forth, that we've started to become used to asking natural questions to, and even in Google searches and things. We see chatbots and virtual assistants, Google Translate, services like automated captioning, which are improving, but they're certainly not at the state that live captioning is at. Then we look at computer perception. Computer vision is probably the most well-known component of that, with applications in autonomous vehicles, self-driving cars, and so forth. There's been work done in, quote, social intelligence. Some call it affective computing, which again has applications in virtual assistants. Anyone remembers Kismet was kind of an early attempt at making an AI robot that can mimic human emotion, facial expressions, and so forth. And then there's general AI, general artificial intelligence, which is really the holy grail of AI. It's not something that we're really anywhere close to yet. All of the individual branches have certainly made a lot of progress, but to kind of combine all of those pieces together, there's still a lot of work to be done. So next, we'll actually talk about the timeline of artificial intelligence. If you received our email that went out earlier this morning with the handout, you might follow along. There are actually significantly more items on that handout than we really have time to go through. I really tried to pick out some of the most outstanding things. One thing that you might notice, a pattern that certainly occurred to me as I was researching this information, is that the frequency of these milestones definitely kind of follows a pattern. If anyone's familiar with Moore's law, the doubling of computer power every 18 months, you can kind of see that in the beginning, these milestones are spaced out, especially the early ones, by a number of years. But as we move closer and closer to the present, these milestones come closer and closer together. That's certainly more apparent in the timeline that's included in the handout. And then even more so, if you actually look at my original source, which is linked on the reference section, the Wikipedia has a timeline of artificial intelligence that really has a tremendous amount of information. So we'll start going back to 1956. The Dartmouth College Summer AI Conference is organized by John McCarthy, Marvin Minsky, Nathan Rochester of IBM, and Claude Shannon. McCarthy coins the term artificial intelligence for the conference. 1979, the Stanford CART, built by Hans Moravec, becomes the first computer-controlled autonomous vehicle when it successfully traverses a chair-filled room and circumnavigates the Stanford AI lab. 1986, the team of Ernst Dickmann at Bundeswehr University of Munich builds the first robotic car driving up to 55 miles per hour on empty streets. 1994, passengers on board the twin robot cars Vamp and Vita 2 of Ernst Dickmann and Daimler-Benz drive more than 1,000 kilometers on a Paris 3-lane highway in standard heavy traffic at speeds up to 130 kilometers per hour. They demonstrate autonomous driving in 3 lanes, convoy driving, and lane changes left and right with autonomous passing of other cars. 1995, quote, No Hands Across America is a semi-autonomous car drove across coast to coast across the United States with computer-controlled steering for 2,797 miles of the 2,849-mile journey. Throttle and brakes were controlled by a human driver. In 1997, you may even remember this event, the IBM Deep Blue chess machine defeats the then world chess champion Garry Kasparov. By the late 1990s, web crawlers and other AI-based information extraction programs become essential in widespread use of the World Wide Web. In 2000, the Nomad robot explores remote regions of Antarctica, looking for meteorite samples. In 2004, NASA's robotic exploration rovers Spirit and Opportunity autonomously navigate the surface of Mars. 2005, recommendation technology based on tracking web activity or media usage brings AI to marketing. In 2009, Google builds an autonomous car. In 2010, Microsoft launched Kinect for Xbox 360, the first gaming device to track human body movement using just a 3D camera and infrared detection, enabling users to play their Xbox 360 wirelessly. The award-winning machine learning for human motion capture technology for this device was developed by the Computer Vision Group at Microsoft Research, Cambridge. In 2011, IBM's Watson computer defeated television game show Jeopardy champions Brad Rutter and Ken Jennings. In 2011 through 2014, so 2011, Apple's Siri. In 2012, Google's Google Now. And 2014, Microsoft Cortana are smartphone apps that use natural language to answer questions, make recommendations, and perform actions. In 2015, Google DeepMind's AlphaGo version fan defeated 3-time European Go champion, two-dan professional Fan Hui by 5 games to 0. In 2017, DeepStack is the first published algorithm to beat human players in imperfect information games, as shown with statistical significance on heads-up no-limit poker. Soon after, the poker AI Libratus by a different research group individually defeated each of its 4 human opponents, among the best players in the world at an extremely high aggregated win rate over a statistically significant sample. In contrast to chess and Go, poker is an imperfect information game. In 2019, DeepMind's Alpha Star reaches Grandmaster level at StarCraft 2. In 2020, in November, AlphaFold 2 by DeepMind from Google, a model that performs predictions of protein structure, won the CASP competition. In 2022, ChatGPT, an AI chatbot developed by OpenAI, debuts in November 2022. It is initially built on top of the GPT 3.5 large language model. While it gains considerable praise for the breadth of its knowledge base, deductive abilities, and human-like fluidity of its natural language responses, it also garners criticism of, among other things, its tendency to hallucinate, a phenomenon in which an AI responds with factually incorrect answers with high confidence. The release triggers widespread public discussion on artificial intelligence and its potential impact on society. So that's, again, like I say, a very brief run through of some of the major milestones in artificial intelligence over the last 50 to almost 70 years, I guess, if we go back to 1956. So let's move forward and we'll start to discuss artificial intelligence and accessibility. So much about accessibility is not clearly defined in such a way that there are simple binary tests for it. So again, think back about how we discussed, Go and chess actually were some of the early successes of artificial intelligence, but these are systems where the number of rules are very finite, the number of possibilities, though to our minds are pretty extensive for a computer, especially with sufficient memory and processing. It's a simple enough task, but the questions of accessibility still require a great deal more human judgment. So it's easy to answer questions like, does this button have a label? Does this image have alt text? Are there captions for this video? But what an accessibility test is really trying to determine is, can a user determine the function of this button without being able to see it? Or will a blind person understand the purpose of or information conveyed by this image? And will a deaf person understand the dialogue heard in this video? So answering those questions still requires a great deal more what we would call human judgment. Again, with as many advances as there have been in AI in these various fields, starting to put them together is still a lot of work. And where it gets deceptive is especially with the large language models and the natural language processing. We easily get the impression, because of the kinds of answers that AI can deliver, that they are much more powerful and think much more like we do than they actually are, because still at their core, these large language models and natural language processing algorithms are very probability based and use a lot of statistical methods to analyze large volumes of written text to come up with the answers that they provide. But at the end of the day, there's no conscious understanding of that information, certainly not in any way that we would understand. So next, let's go ahead and we'll give a quick overview of accessibility and what accessibility is. I want to go over the 4 main principles of accessibility as they're set out in the Web Accessibility Initiative. And those are perceivable, operable, understandable, and robust. So perceivable is fairly self-explanatory. It's just, can the information on a web page or in an application be read or understood? And I'll limit that to actually just saying read, because we'll come back to understood in a moment. That question itself is more binary in most cases. Either there's text on screen that a screen reader can access, that a user with disabilities can still read and see. But that also applies to images, which is an area that is more difficult. Certainly there's been a lot of advance in object recognition in images and computer vision, but knowing what objects are relevant to the context is still really challenging. So if you try to break down the thought process that goes through your mind when you open up a web page and there's some picture, about that relates to an article, there's a lot of very fast intuitive judgments that you make in seeing that information that still has to be explicitly written out algorithmically for a computer to give a user the same information about that image. Otherwise, the best you're going to get is something like 2 people standing in a park on a sunny day, but it probably won't tell you who those people are, why they're standing there, or other details that may or may not be relevant to the context of the information around it. Operable deals with the user being able to make changes, to fill out forms, to activate buttons, to move on to the next step, or to go back, or to clear their information. A lot of the web content accessibility guidelines talk about this in terms of keyboard operability, using touch gestures. So having ways that people who can't use a pointing device, because that's kind of the most common method, so that people using a keyboard only or other means of accessing the web can still have access to make changes and provide input. Understandable is a very challenging guideline, even for humans, as it relates to cognitive disabilities. There are measures of reading ability, but making sure that text is understood and not too complicated, that vocabulary used isn't out of most people's grasp. And then robust is talking about having multiple ways of interacting with information in a web page or an application. So it kind of works hand in hand with operability, but having multiple means of reading information, having alt text for images, having keyboard as well as mouse input and touch gesture input So those cover the basics of the four pillars of accessibility. So what I've done for the next part of our presentation then is found an article that lays out some of the 10 most common accessibility violations or issues that web testers find in terms of accessibility. And what I'm going to do is, first of all, talk about each type of issue that's commonly found and ways that we solve it, and then try to address a little bit of what the specific challenges are for AI to be able to address the same issues. So we'll start, these are kind of broken down into several subcategories. So the first kind of subcategory is links and descriptions. So inappropriate navigation links. Navigation links can pose accessibility issues because screen readers cannot detect them if poorly coded. The screen reader will not skip over it, meaning users with visual impairments will have to listen to the navigation whenever they load a new page. The solution to this problem is accurately assigning ARIA roles to navigation menus to indicate the link's purpose while making it navigable. There should also be a skip to main content link on the web page to allow users to skip navigation. So detecting these issues is generally not a difficulty. Certainly, this is one of the things that come up in automated testing tools like SortSite and Andy and other tools that we talk about and use here at MDOD when we do website testing. But where this gets more challenging for AI is being able to look at a web page in whatever way it does, whether it's using computer vision to look at a fully rendered page or if it's looking at the code, but determining what content is navigational, what content is supplementary, and what content is actually the primary content and most likely to be of interest of somebody browsing the page. And really knowledge of all of that is necessary to code properly. And of course, one way around this is having the initial design incorporate good accessibility practices, which would by default kind of automatically give an AI system information. So using landmarks to denote navigation regions and search regions and main content regions. So if you've made a web page that an AI algorithm can easily identify, likely it's already then equally accessible to a screen reader or user of other access technology. Next, we'll talk about missing or ambiguous link text. So links may be necessary for web navigation only if properly used. It is because missing or ambiguous link text can trigger multiple accessibility issues. For example, missing link text is an obstacle to screen reader users. A typical example of missing alt text is the absence of text on the link. This link can be anything from a button, icon, logo, or any other image. Whatever the link may be, the screen reader user will not read any image that functions as a link without any text. You can avoid the problem by ensuring the image alt text conveys the image purpose or action instead of just having an image description. Even ambiguous or vague text like read more or displaying only the whole link gives the screen reader user a bad experience. this type of text does not convey the required or enough information to the user about what they have to do. Screen reader users tend to navigate from link to link. If there is no link in a text, or if it is ambiguous, it does not provide the user with the link's context and where it takes them. You can once again quickly fix this problem by using informative text, providing minimal details about the link's purpose or function. So very similarly, again, the biggest challenge to ambiguous links or missing link text is that AI models don't really have that human judgment, again, of understanding what the context of the web page is, and the surrounding text or information where the link is located. And so, you know, when AI models advance to the point where they can begin to understand that information, and that quote intelligence can be built into access technology like screen readers, I think that will certainly help in the future. But I think AI's ability to understand a web page in the same way that you or I do as we just look at it is still some way off. The next set of accessibility issues, kind of category of issues, is visuals. So next is inaccurate or absence of text alternatives for images. Is this graphic purely decorative? What meaning is conveyed visually? Does the alt text description convey the same information? We spend certainly segments, and you know, in some cases we could probably devote an entire 1 hour webinar session on composing good alt text and showing examples of good and poor alt text. Images are very problematic and definitely require a lot of human judgment to determine what aspects of an image are actually most important. Because you could, the problem is, of course, a picture is worth 1,000 words, but writing that 1,000-word description is much more likely to be overwhelming and cause a blind user to skip over that information than to find it in any way useful. Whereas somebody who can look at a website visually and just see at a glance, maybe with no other information but the website title or the title of an article that an image is associated with, and immediately certain details about that image are kind of brought to mind. So again, in terms of AI, this really relies heavily on computer vision and the ability to analyze images and detect common objects in images. And certainly we're seeing that we get a lot of press talking about advances such as Facebook generating automatic text descriptions of pictures that people post online. And it's a start for sure, but most of the time the image descriptions that you see are still pretty vague. I guess in some ways maybe people are thankful that there's at least something that says more than graphic or reads just a random alphanumeric file name. But there's usually not information about the names of people in photographs, and things like that might really be more interesting, which on the other hand also raises other interesting ethical and privacy questions. Certainly facial recognition is a part of AI that has also received a lot of press, and there's one could easily pose the question of, do you want AI, especially potentially giving false results, naming an image with somebody's name who that is not actually in that image. But again, we could probably go on for a while, just kind of delving into that. So we'll move on to insufficient color contrast. According to WCAG 2.1, the background and text colors should have a contrast ratio of 4 to 5.1. Sorry, my notes were not quite where they should be on that. Hang on, lost my place now. In the case of small text and 3 to 1 for large text. Sorry if that doesn't quite make sense, but I can try and get that straightened out if you have follow-up questions on what the actual ratios are. Apologies. Similarly, user interactive components and interactive elements like button elements, visible focus indicators, and clickable social media icons should have a color contrast ratio of 3 to 1. The lack of this color contrast can make it challenging for users with visual disabilities like color blindness and low vision to navigate your website. You can prevent this web accessibility issue by using a color contrast checker in the design stage to ensure all text and background colors and interactive elements have the correct color contrast ratio. However, according to WCAG 2.1, user interface components unavailable for user interaction, like a disabled HTML control, need not meet contrast requirements. In this case, an inaccessible, inactive user interface component may be visible, but not operable all the time. The submit button you place at the base of your form is a perfect example. This button may be visible to the reader all the time. However, it gets activated only upon the user completing the required fields in the form. So there are parts of this, again, that lend themselves very well to AI. The ability to for contrast checkers to show the contrast ratio. The challenge is knowing what areas of the screen or the web page actually require those contrast ratios. Is a bigger challenge in knowing the context, whether a control is supposed to be operable or inactive. But again, assuming that it has that judgment of knowing what needs to meet certain contrast requirements, certainly more recent advances, we've seen a lot of examples of code generation from AI tools like ChatGPT. So theoretically, these are again things that down the road can be addressed more easily by artificial intelligence models. The next set of common issues are structural. So a big one is data tables not properly marked up for screen reader users. WCAG 2.0 does not make any distinctions between simple and complex data tables. So users need to associate the information in each data cell with relevant columns and row headers. The simple data tables have one label of row or column headings that are appropriately marked up for screen reader users to access the information in the table. These tables use the TH element for the row and column headers and the TD element for data cells. Screen readers, unfortunately, cannot access data tables with more than one level of row or column headers. The solution to this accessibility issue lies in using more simple data tables because they are easy to mark up. While you can make complex data tables accessible to screen readers by using ID headers and/or scope attributes, most screen reader users find it challenging to use these complex data tables with multiple header levels. So again, this in terms of artificial intelligence addressing these kinds of problems, the real challenges lie in the machine being able to understand the data in the table. And the more easily a machine can understand it, likely, the more easily a screen reader user, for example, can also use their screen reader to navigate and understand the data in the table. But, imagine, using commands to navigate one cell at a time to the left or to the right and maintaining your orientation, especially in complicated tables. So, in terms of the remediation, their point about simplifying and maybe breaking up data into multiple tables instead of trying to consolidate it into a really fancy but really complicated table that would be easy to get lost in, is still really kind of the best solution. And again, really this comes down to human judgment, and I while it's a limitation of AI, just again, the fast progress that we're seeing, I certainly do think that it's possible in the coming years that AI can demonstrate more quote unquote understanding. I can use that term a little bit loosely, but have greater ability to parse out and reorganize complex data tables in such a way that somebody using a screen reader or someone with other cognitive challenges would be able to read and understand. Keeping time in mind, I'm going to try and continue through these as quickly as I can so that if we do have some questions, we can get to those. So I'll do my best here. The next difficulty or challenge that commonly occurs is no logical sequence in focus order of interactive elements. Users who depend on the keyboard alone for navigation purposes should know which element they are focusing on and the sequence of focus order of the interactive elements. Users can get confused and even end up disoriented on the page if there's no logical sequential order for these elements. It is especially challenging for screen reader users with low vision or users with motor disabilities who depend on a joystick for navigation purposes. The solution to this web accessibility issue ensures that users encounter information in focused order relevant to the content meaning while navigating through the content. And of course, the user should also be able to use the keyboard to navigate. And again, as this is addressed by AI, we keep in mind human judgment as to what is logical order. There's not a simple way of asking a computer, well, is this information in a logical order? Because so much of that is either subjective or requires a deeper understanding of what surrounding content is and what order makes the most sense. Common sense, we say logical order, but it's pretty complex logic for a computer to follow. Lack of keyboard accessibility for screen reader users. Again, this one is fairly self-explanatory. Some disabilities make it difficult or impossible to use pointing devices like a mouse to navigate the website. They instead need only a keyboard to move across the website using keyboard commands like the tab key and shortcuts to move to form controls. So for them to be able to navigate your site with a keyboard, it should be easy to access or trigger all the interactive website elements. Includes having well-structured content with the appropriate heading structure. The keyboard should also easily access hyperlinks, forms, links, and media controls. There should also be a visible keyboard focus indicator showing the different page elements. These indicators are visual cues and usually borders or highlights surrounding the focused element that let the user with low vision know where they are on a web page. Besides, you should code the website for keyboard navigation as focus indicators follow a logical reading order. The best and only solution to this problem is ensuring that all your web pages, page content is operable through a mouse should also be operable by keyboard users. So it means that a mouse along with focus and touch events should trigger the interactive elements. So here, supplying the proper coding for triggering events is a pretty straightforward task for AI to perform. I think solving keyboard accessible issues is something that's not too far off for AI. The final couple of issues deal with HTML coding. So missing WAI ARIA attributes. Developer use the help of the Web Accessibility Initiative Accessible Rich Internet Application, WAI ARIA, to build accessible interactive content like sliders, accordions, and drag and drops. However, if improperly implemented, there is the risk of this interactive content interfering with screen reader users' ability to interact with the page. Even dynamic content that suddenly appears on the screen, like confirmation, error status, loading, and warning messages, can cause issues for blind and low vision users. This is because the messages appear without any screen reader announcement. Screen reader users need to be updated about any screen changes because of a lack of visual frame of reference. Besides, they can make informed decisions only if they stay up to date about the current page information. You can, however, quickly resolve this issue depending on the dynamic on-screen content importance and context. You can insert ARIA attributes into your HTML code to appropriately indicate the information. ARIA content notifies assistive technologies that there is a change and lets them understand its content type to navigate the page better. However, as the severity and the increase incidence and impact of these errors depend on the technology used, you will have to test the site on the various operating systems, devices, browsers, and technologies. It helps ensure set automatic focus doesn't interfere with the announcements of newly opened modal windows, loading screens, or pop-ups. Again, this one is more challenging, especially with the need for testing across so many different devices and environments, and does really require a lot of human judgment and decision making. So again, it's a limitation of AI, but you know, as processing increases and machine learning improves, again, it's not beyond the ability of AI. Two more we're going to go through quickly. Forms that do not comply with web content accessibility guidelines. To an extent, I'm not going to go into a deep explanation, but again, the coding of forms, if there's accessibility information missing, is something that I think artificial intelligent models are getting better at identifying code and being able to fix accessibility issues. But the biggest challenge is knowing what fixes to make that are content and context dependent. And then the final accessibility problem lies in non-HTML content limiting web accessibility. And so this is a lot to do with XML, metadata handling, web apps, etc., as well as document accessibility. So when websites link to PDFs, Word, or Excel, or other third-party files, that brings in the whole question of document accessibility, which there are parts of that artificial intelligence can address, but parts that really rely a lot on human judgment. That again, the technology is definitely not there yet, but difficult to predict when and how quickly that may change. So that leads us to the end of our presentation. We do have just a couple of minutes left. We have our contact information on the screen. The website for MDTAP is here, www.mdtap.org. And you can reach Stephen Polacek and myself, who work in the MDTAP office at mdod.nva@maryland.gov. And of course, our previous webinars, as well as this one, will be available on our YouTube channel. So, Stephen, I don't know if if folks have questions that they may have posted in the chat or in the Q&A section. We can maybe try and address them in the last couple of minutes.
Yeah, so far I'm not seeing any, but everyone, if you have questions, feel free to put them here. Oh, we just got one. How is AI actually incorporated? How would I start? Is it a website or app to initiate a project? Are you using it?
So we're doing things very manually. We do have some tools that have automated ability to check for problems. So I guess to an extent you can call that AI. It's kind of a blurry line because the tools we use are all pre-programmed. There's no machine learning where as it analyzes more data, the computer gets better at identifying issues. But we use tools like SortSite and Andy that can identify a number of accessibility issues, but most of them don't have the capability of actually fixing code. Some of what I referred to earlier has to do with OpenAI's ChatGPT, and there's a lot of articles about people using ChatGPT to write code modules. And I have not done any experimentation with it directly. I don't have a sufficient knowledge of coding to even understand if I asked it to write code for something, whether that code would be accessible or not. So I just don't have enough of the background on that development side to actually test how that might work. But again, ChatGPT, generally speaking, and other similar chat programs that are now available, Google Bard is the other one that I can think of, do have the ability. You can instruct them to write code or modules of code. And I suspect you could provide a snippet of code and ask it questions about whether it's accessible or how it could remediate it for accessibility. So that things like that would be interesting to investigate further. I think that's a good question.
Yeah, I do know it's a hot topic. Sorry to throw in here, but it's a hot topic in like a lot of accessibility conferences. And I know of services that are offering like AI solutions, but they're kind of in the same vein as what Matt said, where they'll review the code and try and fix it, but they can't fix the subjective judgment parts.
Which leads to questions about overlays, which is almost its own separate accessibility topic. I didn't want to necessarily open that can of worms. However, yeah, there are several companies who write overlays that can be basically snippets of code that you add to the beginning of your website that link it back to their tools that may do a lot of automated remediation. And there's a lot of subjective judgment as to how effective those are. And in many instances, I've personally seen where using the accessibility overlay actually makes for a worse and less accessible experience.
Second question here. When you mention web apps having issues with accessibility, any certain languages used in building them worse than others?
That is a really good question that I don't have an answer to. I don't really have a compilation of what languages are used. Stephen, you and I were both in actually the ARC session yesterday, and they talked a little bit about Bootstrap. I'm not that familiar with those and React and some of those environments. But I recall them talking about Bootstrap having some of the least accessibility issues. But it's designed for more static websites too. So the more complex and the more interactive, the likelihood of accessibility issues increases. I don't know if you have any insights to add to that or not.
Only from, I guess, previous experience testing apps created with those languages. It seems to come down more to good implementation than the language itself, because like ultimately you're going to end up having to use something like ARIA to make it work with assistive technology like screen readers and such. So you can make something in Bootstrap or in React, and they might still be usable, but ultimately you're going to have to end up doing additional work to make it fully accessible and interactive. So yeah, as Matt said, the more complex it becomes, the more you have to work with that and really know ARIA to make sure it works correctly. So I wouldn't say that there's any certain language to avoid other than like, the typical things that you'll hear depending on which programmer you're talking to. Everyone has very distinctive opinions about, Python versus Java versus React or whatever. I've seen all of them be accessible and I've seen all of them not be accessible. So it really comes down to implementation.
And related to implementation, the one thing that I might add is the more you customize something, the more you change it from the original code out of the box, the more chance you have of injecting accessibility problems, because out of the box, most of these components are designed to be accessible.
Are there any other questions before we call it?
Once again, I want to thank everyone. Thank you, Stephen, for your assistance with running the slideshow. My colleague, Stephen Polacek, was with us today. Thank you for joining us for this webinar, and we will see you again next month.